Hello, today we'll be talking about implicit differentiation and how to find it. Okay, first we need to start off with functions versus relations. So functions look something like this. You will have like y equals or f of x equals then your function on this side. Notice on this side there's the only variable used is x. E is not a variable, that's a constant. It's a very specific value. There's one y value for each x value you plug in. So if you plug in one x value, you won't get two y values out. And y and x are on separate sides. Now here we have a relation. So first of all, the first thing you might notice is that you have 2 times x to the power of y. You don't really see x and y being right next to each other like that. And then you also here you have 2 times pi times y, and then it equals 4 times y to the power of x. So what this is allowing you to do is you can plug any x value, but there might be more than one y value as an option. And y and x can be on the same side. And one other thing you can notice is what the graphs look like. So here is our function from before. You notice it's a little bit weird. First of all, you start shooting straight up, and then you start coming back down immediately right around x equals 5 3/4. But there's only one y value for each x value plug in. 2 x values may have the same y value, but each x value has one individual one y value. So if you just draw a line for each x value, it won't cross the function more than once. A relation, however, let me move my camera. There we go. Now you can see the whole thing. Now a relation from before, this monstrosity. Now you see that you have this part. There's a line going up to going straight to infinity. But then you also see that around here, or actually this whole part, there's actually 2 separate y and x and y values. So if you draw a line, let's say we draw a line at x equals 40, you draw it straight down. Oh, we pass through it around y equals 40, but we also pass through it around y equals 2.5. So that's just showing that relations, they don't exactly follow the rules of functions. You can do a lot of crazy stuff with this. And the goal of this video is to show that you can still find the derivative of this. You just need to do a little bit more stuff to it. Notation used, dy over dx is derivative of y with respect to x. We're going to be using that a lot because we have we have 2 variables and we want to find the derivative. So we use derivative of y. So I will write y apostrophe to save space, and the apostrophe means derivative of. And one more essential, the chain rule. This will be essential when we are finding derivative of stuff with y in it. So we have h of x equals f of g of x. And then its derivative is the derivative of the outer function with respect to the inner function times the derivative of the inner function. And the reason why this is helpful is because in our case, y is going to be our inner function because it is a function with respect to x. So it means it's going to be our derivative of the outer function with the respect to y times the derivative of y. Okay, let's do our first example. This is called Descartes' folium. So we get this. It's a very nice looking function, and I made one right here as well on Desmos. Now this has an equation x to the power 3 plus y to the power 3 equals 3 times x times y. So first thing you notice, this is a relation, not only because you can see it on the graph, in this part you're actually going through 3 separate y values, but over here you got x and y on the same side, you have x multiplied by y, and you want to find the derivative of this. So how do you do that? Well, what we do is we find the derivative of each part. So let's first start with x to the power 3, that goes to 3 times x to the power 2, power rule, and now let's do y to the power 3. So this is where chain rule comes in. Y is our inside function. X to the power 3 is our outside function. So it equals 3 times y squared. That's the first part. And then it's multiplied by the derivative of y. And this equals the derivative of the other side. So what we do is I just take out the 3. Find the derivative of the inside part. That's y, because derivative of x is 1. Plus x times the derivative of y. Okay, and now what we have to do is we have to solve for the derivative of y, dy over dx. So first thing we do, we have our the derivative from before. Now what a lot of people would do is they would distribute this out, then divide by 3. But what you should notice is that you can just straight up divide by 3 here, divide by 3 here, divide by 3 here. You don't need to distribute. It's a very helpful thing to know, and it helps you get through the problem a lot quicker. Now we have x squared plus y squared times the y derivative equals y plus x y derivative. Now we move everything with y derivative to one side, everything without it to the other. It's just like solving for x. Now we factor out the y derivative on this side, and then we divide by this remaining part to move it to the other side, which means the derivative for Descartes' folium is y minus x squared divided by y squared minus x. So the way this works, let's open up Desmos. So here's our function. X cubed plus y cubed equals 3 times xy. X cubed plus y cubed equals 3 times xy. Okay, that's a very different function. So this is what we have. So let's say we want to find the derivative at, let's say, here. Can I click on the function? Not. Let's approximate. Where can we just find the derivative of it? Equals 2, x equals 1. So if we were to find the derivative of this point, let's do this tiny part down here. We have to use the derivative that we found, which is y dot equals y minus x squared divided by y squared minus x. So we know our x value, which is 1. Okay. And now if we knew what the y value was, we would plug it in here. I don't know, let's say it is 0.35. I know that's not actually the value, but let's assume that we're just approximating it. 0.35. Let us remove this. And that means at this point the slope of the tangent line is roughly 0.74. And then that means you can draw tangent lines using this. And here's one that we can actually do. Let's go back to our derivative function. Okay. So, over here, x equals 1.5. We have a solid value. It's going to be 1.5, 1.5. So let us plug in our x and y values. And this should result with -1. And now we can do, because now we know the derivative of that point, you could say y minus 1.5. This is point slip form. Y minus 1.5 equals negative 1, or just negative, times minus 1.5. Now, because of this, we now know the tangent line at this point. If we didn't have implicit differentiation, we we're going to have to go through a whole thing of finding a way to remove the y from this side and move it over to this side. And we do not want to do that because it's hard. I mean, there are going to be some cases where you have to, but in this case we don't have to because we can figure out the derivative in another way. Okay, so our second one, this one all fit on one page. This is a rotated ellipse. I just found values that would create an ellipse. So we have x squared plus y squared minus xy plus 16x plus 25y plus 9 equals 0. If it weren't for this minus xy, you would have thought this was some kind of a circle or some kind of ellipse. Now what we can do is we can find the derivative of x squared, find the derivative of y squared. Remember the chain rule. Find the derivative of x times y. Remember to keep the minus sign in, so we distribute it across. Find the derivative of 16x, which is just 16. Find the derivative of 25y, which is 25 times the derivative of y. Derivative of 9 is 0, and derivative of 0 is 0. That's also an essential. I know people who've accidentally written derivative of 9 is 9, and that's not good. So now what we do, we just do the same thing as before. We move over all the stuff with y derivative in it to one side, everything without to another side, factor out the y derivative, then divide. That means the derivative of this function is 16 minus 2x plus y divided by 2y minus x plus 25. And let's see if I can recreate this function. X squared plus y squared minus xy plus 16x minus 25x plus 9 equals 0. This should be a plus 25. There we go. So this is our function. So let's try to find a point where we can find the derivative of. Okay, let's try to approximate the derivative at any point. Maybe here. Let's try here, because this one we have a solid value. Okay, so if we know that our derivative function is going to be 16 minus 2x minus y, this is all divided by 2y minus x plus 25. Now let's start plugging in values. Y is going to be equal to 0. Remove all of this. Okay. And now we can replace x with negative 40.779. This should be a good approximation, negative 40.779. There we go. And that's saying our derivative at this point is around 1.5. Maybe keep on zooming in. It starts to look a little bit more and more like it. Actually, it looks more like a 1-to-1 ratio. Maybe it's because of how our numbers are written that the approximation isn't that good. Because the more numbers we add to it, the smaller the slope gets. Okay, so I hope you now understand what implicit differentiation helps with. So you got relations like this monstrosity over here. You can find the derivative of it. And over here, notation, we use dy over dx equals the derivative of y with respect to x. I just use y apostrophe to save space. And it also means derivative of. Then we remember that we have to use the chain rule, because y is a function of x, so it's essentially the inside function. and we went through Folium Descartes, and then a rotative ellipse, and we found the derivatives of each, and then we figured out how we can use them. Okay, so I hope you enjoyed this video. Like and subscribe. Send this to anyone if they need help, and I'll see you soon. Bye.